Okay, so what we're going to do is we're going to do a wee experiment to show that Hess's law is actually true. So what I've got here in my test tube, which is not a test tube, it's a beaker, which is not a beaker, it's a measuring cylinder. This is some hydrochloric acid, and we're going to add that into some potassium hydroxide. And that's a one-step reaction. It's going from the solid potassium hydroxide, and it's going to do a neutralisation reaction with the acid. Now, to work out the enthalpy change, we need to measure the initial temperature of the acid, and then we'll measure it again after we've added it to the alkali. So I'm going to measure the temperature of the acid first. It should be about 19 degrees, so remember that figure. My cameraman's just going to have a look at that. 19 degrees. So what I'm going to do is I'm going to add in my pre-weighed 2.53 grams of potassium hydroxide into my polystyrene cup. We're using a polystyrene cup here with a lid to minimise any heat loss. Then what I'm going to do is I'm going to add the acid to the potassium hydroxide, and then I'm going to put the lid quickly on to minimise any heat loss, and then I'm going to put my thermometer in and we're going to measure the highest temperature. You can see it's still going up. Still going up. Looks as if it's kind of slowing down a wee bit. That looks to me to be about 28 degrees Celsius, and I do not think it's changing from that. So my temperature change then is going to be 8 and 1, so that's going to be 9 degrees Celsius. T1 is 9 degrees Celsius. You can pause it again. So now we're going to have a look at the second route, and that involves dissolving the potassium hydroxide in water first, and then doing the neutralisation with the acid. Okay, so that's going to be two energy changes, one for dissolving it, and then one for neutralising it with the acid. So what we're going to do is we're going to measure the initial temperature of our water here. And that is saying about 18 degrees Celsius. That might be difficult to see, but it's definitely saying 18 degrees Celsius. Okay, so what I'm going to do is I'm going to add my pre-weighed, this is also 2.53 grams of potassium hydroxide. I'm going to add that into the polystyrene cup. And then I'm going to very quickly add my water. And then I might actually stir this a wee bit before I put the lid on, just to make sure it's dissolved properly. Then I'm going to quickly put my lid on, and then measure the temperature. The temperature looks as if it is increasing. I would maybe say to about 20 degrees Celsius. Maybe leave it a wee bit longer just in case. Okay, I'm happy with 20 degrees Celsius. Okay, what we're going to do now is we're going to do our next step of our reaction, which involves adding the acid. So this is an enthalpy of neutralisation here. I'm going to neutralise that potassium hydroxide and then measure the temperature again. And that is increasing again. And I expect this to be slightly less this time because we're using more water, so the mass that we're actually heating here is going to be more, so it will require, there will be less of a temperature change for the same amount of energy. That looks as if it's going up to 25 degrees Celsius. Cool. As we can see here, we've worked out the temperature change to be 9 degrees for the first route, which gives us an enthalpy change of minus 1.881 kilojoules. If we look at route 2, which is delta H2, that was for when we dissolved it, that gave us a temperature change of 1 degrees, and that ended up being an energy change of minus 0.209 kilojoules. If we look at the third one, one thing is different is because we then added 50 mils of hydrochloric acid to 50 mils of the solution we had made. That changes the mass of water to 0.1, because it's 100 mils, then you divide that by 1,000 to get it into kilograms. And then I misread the thermometer, and actually it was 4 degrees Celsius. So that ends up being minus 1.672 kilojoules. When you add them together, you get minus 1.881 kilojoules, which is the same as route 1, which proves that Hess's law is correct. Thank you.